So here's a little story about why, if you have mixed up customer data, you need a graph database. Have a look at the diagram on the right. You have a database with 3 customers: Bob Smith, Robert Smith, and Bobby Smith. Bob is male, has a birthday on the 1st of January and a phone number ending 567. Bobby shares a phone number with Bob, but is female and her birthday is on December the 31st. Robert is male with the same birthday as Bob, but his phone number is different. It ends 432. The question is, are they all the same person? Making sense of and deduplicating customer data is a real problem, and it's not easy, but it's not so hard for a graph database. Because a graph database joins the data together at the time it's formed, it can very easily count the entities that Bob, Robert and Bobby have in common and use that information to make an optimal guess about who they are. In this diagram, I've split the Smith name icon into 3 to make the explanation clearer, but it's all the same data. I haven't changed anything. Okay, let's start with Bob and Bobby. They share a phone number and a surname, but they have different birthdays and they are different genders. So they have 2 things in common, but they each have 2 attributes they don't share with one another. Bob and Robert share 3 things in common: surname, gender and birthday, but they have different phone numbers. Robert and Bobby only share a surname, but their gender, birthday and phone numbers are all different. It's beginning to look like Bob and Robert are the same person, but Bobby is someone else. Let's go a bit further. A graph database can easily put a weighting on how important a shared attribute is. I've shown this on the diagram by increasing the size of some icons and reducing the size of others. You can add up the average weighted score between each person, and this would support the theory that Bob and Robert are duplicates. In fact, in real life, you're going to be deduplicating between large sets of people. And instead of finding pairs, as in this case, you're going to be looking for small sets of people who are all likely to be the same. Graphs can easily do this using a weakly connected component algorithm, which I've shown on this with a dotted line. What we've actually shown here is a pretty complicated logical operation made simple by the fact that a graph database can count the number of links between entities. Doing it on a conventional database is actually surprisingly hard. Have a look at the tables on the left. It's actually exactly the same information, but you have to look pretty hard at it to work it out. To find the duplicates, you have to join the database on the left to itself on each of its fields. So you have to join first name to itself, and then you have to join last name to itself, and sex to itself, and so on and so on. And then you need to union all the information together. This is going to end up in a really, really big data set. And you still have the problem of how then to choose which people you're going to merge together. This is not straightforward. When you decide to merge 2 records, for example, Bob and Robert, then the decision will have an effect on the other entities closely connected to them, like Bobby. And where you merge Bobby into, you may have a knock-on effect on all the other records in your database. The order in which you do it is critical. Now, the local structure of a graph makes those decisions easy, whereas the huge data set of potential matches that you've created through the table joins is much harder to resolve. So, it's no wonder that without a graph database, deduplication is such a hard problem for customer-facing businesses. There you go. One of many cases where you can do things in a graph that you simply can't do with a conventional database.